In this lecture, we want to begin our examination of sorting algorithms. In this first lecture, we're going to look at the slower sort algorithms. We can divide sorting algorithms into two broad groups. Slow algorithms that typically have complexity big O of n squared in all cases, and fast algorithms that are in little o of n squared, or they are faster than n squared. Typically, these are n log n. The difference in the amount of time a sort takes can be quite dramatic depending on the algorithm. The difference between the slow and fast group is striking. So here's a simple chart to demonstrate the difference between the two. Bubble sort is actually the worst of the n squared algorithms. Quick sort, probably the best of the n log n or fast algorithms. So notice as we increase the size of the array, the time increases dramatically with the bubble sort. That is, as you know, when you double the input size, the time should take 4 times as long. And so you can see here where we go from 20,000 to 40,000, we go from roughly 1 second to 4 seconds. And then when we go from 40,000 to 80,000, we go from 4.5 seconds to 18 seconds. So these are roughly 4x. But this, the quicksort algorithm, grows much more slowly, as you can see. Notice that with an array of size 320,000, bubble sort takes about 5 minutes, whereas the quicksort algorithm is about a 1/20th of a second. 5/100ths of a second is how long it takes. So this is quite a dramatic difference. We should comment here that with small arrays it really doesn't matter. That is, you might be thinking, why would anyone ever use a slow algorithm because the n log n algorithms are so much faster? Is there a place for the n squared algorithms at all in a program? And the answer is yes, there is, because they are so much simpler. The code for bubble sort, selection sort, insertion sort, which are the algorithms we are looking at in this lecture, the code is so much simpler than the faster algorithms. Therefore, it's a good idea. Simple code is better than complex code. So if you're going to sort an array that's never larger than, say, a couple of hundred elements, then the times will be less than 1/10 of a second no matter which algorithm you use. Then it isn't really going to matter. And in these cases, simple code is better than complex code. However, if the array size is unknown or large, then you want to avoid these slower algorithms. There are two other important characteristics to consider with sorting algorithms, and this applies to all of the sort algorithms. Those two things are stable and in place. The term stable refers to how the sort algorithm deals with duplicate elements. As an example, suppose you're sorting an array of class person, and you have 2 Smiths in the array, 2 people with the last name of Smith. They're obviously not exactly the same person. They're 2 different people. They just have the same last name. Stable means that the ordering of the 2 Smiths in the original array is retained, that once it's sorted, their ordering hasn't changed. That is, Smith is equal to Smith, therefore those 2 array elements are considered equal, but the original ordering is retained such that the Smith that occurred first in the unsorted array occurs first in the sorted array. The second term that is of great importance here is in place. In place means that the algorithm does not require any extra memory in terms of the input size n. And that last phrase is really important. That is to say that virtually all sorting algorithms require some kind of additional storage or temporary variables. However, that's not in place. So an example of in place would be something like the merge sort algorithm, which we will look at in the next lecture. The merge sort algorithm requires that you make a copy of the array. If you have to make a copy of the array, then the amount of memory required for the copy is very much dependent on the input size n. If you have an array of size 100, the copy is going to be size 100. If you have an array of size 1 million, the copy is going to be size 1 million. Therefore, the amount of extra storage required changes in terms of the input size n. However, if you have an algorithm that simply has 1 or 2 or 3 temporary variables, but you always have the same temporary variables no matter how large the array is, then that algorithm is in place. When we look at sorting algorithms, it's important to consider the best, average, and the worst case scenarios. That is, the performance can differ dramatically depending on how the array is ordered to begin with. For example, if you have an array that's in sorted order, then insertion sort is big O of n, not n squared. In fact, big O of n is better than big O of n log n. So, in fact, if the array is already in order, this algorithm will run more quickly than the best of the n log n algorithms. It's faster. So, insertion sort is the algorithm of choice in the case where the array is in either sorted or almost sorted order. This occurs fairly frequently. You might have a business with an array of customers, say the utility company, and you have an array of your customers and they're in sorted order. But each day you have people come in and sign up for service. They have moved to the community and they need to get utility service. So you may have a few dozen records tacked on to the end of an array of size 1 million. To resort that array and include the new records that are tacked on to the end, insertion sort would be much better than using one of the n log n algorithms. It would be faster. However, this isn't always the case, certainly not for all algorithms. It turns out that the array in already sorted order is the worst case for the quicksort algorithm. So the quicksort algorithm is important because it is the fastest one for general purpose sorting that we have. When I say fastest, I mean wall clock or empirical times, not complexity. There are several algorithms that are n log n, and quicksort is one of those. However, in the average case, the wall clock time for quicksort will be better than the other algorithms. But this algorithm, quicksort, has its worst case with an array that's in already sorted order. In this case, the performance descends to big O of n squared. Thus, the best, average, and worst cases may vary, and it depends on the algorithm itself. The three slow algorithms we're looking at here. For bubble sort and selection sort, the best, average, and worst cases are the same. They're big O of n squared. Insertion sort is the fastest of these three slow algorithms in terms of wall clock time. But in the best case, where you have an array that's already sorted, then the complexity is big O of n. Typically, these n-squared algorithms have an outer loop that runs n times and then an inner loop that runs up to n-1 times. And so these algorithms will typically perform n-1 plus n-2 plus n-3 down to 1 comparisons. And this is an identity. We have n times n-1 over 2. And this, of course, is n squared in complexity. So what I want to do now is look at each of these three algorithms in turn and examine how they work. We want to look at the mechanisms that they use. So here we have a small array we will use to demonstrate bubble sort. The way bubble sort works is you start here and examine the first two elements in the array. And if they're out of order, you swap them. That is, the 2 is smaller than the 19, so these two need to be swapped. And then you move down to the next set and compare them. Then you move down to the next set and compare them. Next set, next set, next set. And so you do the comparisons this way, and what you end up doing is moving or bubbling the largest element in the array down to the end. So in this array, we can see that the 33 is the largest element. So after the first pass of this algorithm, the 33 will be at the end. Okay, so the first pass, we begin and we compare the 2 and 19, and they're out of whack, so we swap them. So we have 2, 19, 23, 16, 33, 4, 27, and 1. Now we move down to the next pair. The 19 and the 23, and they're okay. The 19 is smaller than the 23, so we move down to the next pair. And these are out of order, they must be swapped. So we swap the 16 and the 23, we have 2, 19, 16, 23, 33, 4, 27, and 1. Now we move down to the next pair, and the 23 and 33 are okay. So we move down to the next pair. The 4 and the 33, these are out of order. They must be swapped. 4 is smaller than a 33. So we have 2, 19, 16, 23, 4, 33, 27, and 1. Now we move down to the next pair, and they're out of order. The 27 is smaller than the 33. They must be swapped. So we have 2, 19, 16, 23, 4, 27, 33, and 1. Finally, the final comparison here. The 1 is smaller than the 33. It's out of place. They must be swapped. So we have 2, 19, 16, 23, 4, 27, 1, and 33. And thus this is the end of the line here. That is the first pass of the outer loop. Notice what has happened here. The largest element in the array is now at the end where it belongs. So how many comparisons did we do? We compared the first pair. There's 1, 2, 3, 4, 5, 6, 7. There are 8 elements in the array. We did 7 comparisons. All right, obviously the array is not in sorted order, though the largest element in the array is now at the end. So we have to go again. So we go again and we compare the 2 and the 19, and they're fine. We compare the 19 and the 16, and they're not fine. They're out of order. We must swap them. So we have 2, 16, 19, 23, 4, 27, 1, and then the 33. And this part of the array is sorted. Okay. Now we compare the next set. We have 19 and 23, and they're okay. We have 23 and 4, and they are not okay, so we swap. 2, 16, 19, 4, 23, 27, 1, and finally the 33. Now we compare the next set. The 23 and the 27, and they're okay. 23 is smaller than 27, so we don't do any swapping. We move down to the next pair. 1 and 27 are out of order. They require swapping. 2, 16, 19, 4, 23, 1, 27, 33. So again, notice what has happened. There are now 2 elements in the sorted partition of the array. That is, the 33 is the largest element in the array. The 27 is the next to largest element in the array. So everything that remains to the left here is smaller. So this part of the array here, the sorted partition, increases by 1 every time. Now, how many comparisons did we do this time? We compared this set, that's 1, 2, 3, 4, 5, 6. We did 6 comparisons this time. So the array has 8 elements. We do 7, then 6, and of course the next pass we're going to do 5. So starting again, we have 2 and 16, and that's fine. We go down to the next set. We have 16 and 19, and that's fine. We go down and we see 19 and 4, not fine. We have to swap them. The 4 is smaller than the 19. So we have 2, 16, 4, 19, 23, 1, 27, and 33. Now we move down to the next set, the next pair. 19 and 23, those are fine. We don't have to swap. We move down to the next pair. 23 and 1 are out of place. The 1 is smaller than the 23. We need to swap. We have 2, 16, 4, 19, 1, 23, 27, and 33. So we have added one more to the sorted partition. Here, out of the unsorted group that we started with, we moved the 27 into place here. This group, the 23 is the largest one, and it is now in position. This time we did 5 compares. Now going again, we have 2 and 16, that's fine. 16 and 4 are not fine, those have to be swapped. This gives me 2, 4, 16, 19, 1, 23, 27, and 33. Okay, we did the 16 and the 4 here, so we move down to the next set, the 16 and the 19, and they're in order, there's no problem. We don't swap them, we move down to the next pair, the 19 and the 1, and they are out of order. 1 is smaller than 19, so we have to swap. We have 2, 4, 16, 1, 19, 23, 27, 33. And now this part of the array, the sorted partition as it were, contains 4 elements. So with each pass of the outer loop, we add 1 to the array that's in sorted order. Now we go again. The 2 and the 4 are okay. The 4 and the 16 are okay. The 16 and the 1 are not okay, therefore we must swap them. We have 2, 4, 1, 16, 19, 23, 27, and 33. So we now have added one more to the sorted section. Going again, the 2 and the 4 are okay, the 4 and the 1 are not okay. So we have 2, 1, 4, 16, 19, 23, 27, and 33. And again, we've added one more to the sorted partition. Finally, We compare these guys and they're out of order. We swap them. We have 1, 2, 4, 16, 19, 23, 27, 33, and the array is now sorted. So the number of comparisons we had is 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1. So this gives us n times n minus 1 over 2, which is equal to big O of n squared. Notice that in some cases we didn't swap, in other cases we did. It depended on the ordering of the elements, but we did a comparison for all of these cases. Therefore, in every case, regardless of how the array is initially ordered, in every case we're going to do the same number of comparisons for an array of a specific size. So this is the worst general purpose algorithms in terms of wall clock time. And what makes this the worst is that the elements move very slowly into place. For instance, consider that we had a 1 as the last element in the array here. And this 1 moved forward 1 position each time. Here it's in the last position. Now it's in the second to last position, third to last, fourth to last, and so on. So this 1 moves forward 1 position with each pass of the outer loop. So it moves very slowly. More importantly, how many times did we swap it? We swapped it here, 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 and here, and finally here. Therefore, we have moved this 1 7 times. So this is woefully inefficient, and there are better ways of doing it. Is this algorithm stable? Yes, it is. If we had duplicate elements, we simply wouldn't swap them, and therefore they would retain their initial ordering or initial position. Is it in place? Yes, it is in place because no additional storage is required. We just simply scan down and swap the elements if they're out of order, and the swap does require 1 additional variable. However, this does not increase as the size of the array increases. Therefore, this algorithm is both stable and in place, though it has little else to recommend it. The next algorithm that we want to consider is selection sort. So using our same initial array, we're going to look at selection sort. The way selection sort works is you scan down the array looking for the largest element in the array. 19, 2, 23. And so you do something like this. You have a variable best so far, and you set it to the first element in the array, 19, and it's at index 0. Is the 2 any better? No. We're looking for, again, the largest element in the array. So the 2 is not larger than the 19. 23, oh, the 23 is larger. Okay, we've got a new best so far. We have the 23. At index 2, that one's better. 16, nope. 33, yes, the 33 is better. We have the 33 at index 0, 1, 2, 3, 4. We look at the 4, the 27, and the 1. And so 33 is the largest element in the array. So we swap the end element, whatever it is, with the 33. That is, the 33 goes here, and this element goes here. So we don't care what's in last position. We know it's not the largest one, so we move it. 19, 2, 23, 16, 1, 4, 27, and finally 33. So we have the same idea here. The 33 is at the end. It's in last position where it goes. However, notice that we didn't bubble it down. We didn't waste time giving it extra swaps. So I think you can see this is much more efficient than comparing adjacent elements and swapping them if necessary. So let's do the next pass. We scan down the array and we look for the largest element in the unsorted section of the array, and it's the 27. So we can include now the 27 in the sorted partition. So the algorithm would actually swap the 27 and the 27, which is okay. So now, having placed the 27, we scan down the array and look for the largest element, 19, 2, 23, 16, 1, 4. So the 23 is the largest element in the array. So we swap the 23 with the element at the end, which is a 4. We now have 19, 2, 4, 16, 1, 23, 27, and 33. Again we go. We scan down the array. 19, 2, 4, 16, 1. 19 is the largest element. We swap the 19 and the 1. We have 1, 2, 4, 16, 19, 23, 27, and 33. Going again, 16 is the largest element, and then the rest of it is in order now. It's sorted. Of course, you go through the motions you have to check. Therefore, the array is now sorted. So I think you can see that this algorithm is better than bubble sort. It's better than bubble sort, but we can do better yet. The next algorithm is an improvement on this one. What makes this better than bubble sort is the fact that there's a single swap that occurs with each pass of the loop. Thus, you scan down looking for the largest element in the unsorted part of the array, and then you swap it with the in position. So there's one swap with each pass of the outer loop, so you don't end up removing things repeatedly. So in the case of bubble sort, the 1 was moved every time. So the 1 went from last position to next to last, to here, to here, to here, to here. We moved it one place, one position forward until it got into the final position. But with this algorithm, when we moved the 19 and the 1, it landed here. So there's a single swap for every pass of the outer loop, which makes this more efficient. So where could we improve on this algorithm? Well, what's costly here is examining every element in the unsorted part of the array every time. That means that we have to look at n-1 elements, and then n-2, and then n-3, and then n-4, up to 1, which means we're actually doing the same number of comparisons here. It's the fact that we have to look at every single element in the unsorted partition every time that's expensive. We are saving by not doing all of the swaps. However, this algorithm is not as efficient as it might be. So even though there are fewer swaps, the complexity is the same, and this algorithm is n squared. So if we can find a way to avoid examining every single element in the unsorted part of the array every time, we will gain more efficiency. And so that's the next algorithm we want to look at. The next one we want to examine is insertion sort. So starting again with our same initial array, we want to look at insertion sort. Now the idea of insertion sort is a fairly simple one. We want to start at index 1, not 0 but 1 here. And now we're going to have a temporary variable where we copy this out and then we overwrite it. We shift things down until we find the spot where it goes, and then we drop this temp2 in. So as we do this, we have the temp2. So the first pass is this. We compare the 19 and the 2 to see if we need to move it down, and we do. So now we have 19, 19, 23, 16, 33, 4, 27, and 1. And then once we finish that pass, we drop in the 2. So that's the first pass of the loop. Next pass. So now the 2 and the 19 are in sorted order. Now we need to insert the 23. So we look at the 19, and if we need to, we're going to shift it. So what we have done, here we have temp, and it's this 23. And then the idea is we start shifting, and we move things over until we find the spot where the 23 goes, and we drop it in. Well, it is where it goes. There's no shifting necessary. So notice that with this algorithm, we did not examine all of the elements in either the sorted or unsorted part of the array at all. Rather, we examined one element and stopped. The 16. So we put the 16 in temp, and we're going to override it is what we will do. So we're going to shift this down until we find the place where it goes. So what we will now have is 2, 19, 23, 23, 33, 4, 27, 1. We will have 2, 19, 19, 23, 33, 4, 27, and 1. And we have reached the spot where it goes, so we drop in the 16 right here. And now we have 4 elements in the sorted part of the array. Now we insert the 33. Well, it's larger than 23, so no shifting is necessary. So we simply skip the inner loop entirely. There's no movement necessary. The next one, of course, is the 4. So again, we put 4 here in temp, and we start shifting. So we move the 33 here, the 23 here, the 19 here, the 16 here. So what this looks like before we drop in the 4 is 2, 16, 16, 19, 23, 33, 27, and 1. So then the final step here is to drop in the 4 here. And now we have our array with 6 elements. Now we insert the 27. So again, we take this 27 and copy it into temp, and then just overwrite it. So the 33 goes here. And of course what we're doing is looking at each element in turn, and we stop when the element we're looking at is smaller than what's being inserted. Well, the 23 is smaller than the 27, so we stop. And so what we now have is 2, 4, 16, 19, 23, 33, 33, and 1. Now we drop the 27 in where we stopped. We drop the 27 in right here. And then we are at the last element in the array, the 1. So again, we start shifting. We shift the 33, the 27, the 23, the 19, the 16, the 4, the 2. So we end up with 2, 2, 4, 16, 19, 23, 27, and 33. And at that point, we fall out of the inner loop, and here we write the 1. And our array is now in sorted order. Now then, is this stable? Yes, it is. It's stable because as you're shifting down this way to insert, if the elements are identical, you don't shift it. Therefore, the ordering is preserved. Is it in place? Yes, it is. No copies are necessary. We really only have this one temporary variable, and it's the same temporary variable whether you have 10 elements or 10,000 elements. Therefore, this algorithm is both stable and in place. So selection sort is not stable. Why is it not stable? I want to take a look here and show you why this is the case. So I've written an array here. Consider this case. We scan down the array and we find the largest element and we swap it with the element in last position. What happens when we do this? Apologies. What happens when we do this? We move the 2, we swap the 2 and the 14. We now have 6, 3, 2, 1, 2, 7, and 14. Notice that we have 2 2s here, but these have been flipped. These have been flipped because this is the first 2 and this is the second 2, but now this is the second 2 and this is the first 2. So anytime you have an algorithm that swaps elements without looking at them, without considering what they might be, you have this concern and this problem. Whenever you just swap them without looking at it. That is, the 2 is not examined at all. Rather, we swap the 14 with whatever we found in last position. And so what we have done is we have broken the stability of this. We have flipped the order of the 2 2s that are in the array. So this makes this algorithm not stable. This turns out to be an important factor, and there are times when this behavior is critical. Notice that of all these algorithms, only selection sort is not stable. With the exception of the stability of selection sort, these algorithms are stable and in place. It turns out that the faster algorithms don't have these characteristics. They are either stable or in place, but not both. And it turns out, in fact, that insertion sort here is the fastest algorithm that is both stable and in place. So for the faster algorithms, you're going to have to sacrifice stability, which means that duplicate elements will not be in the same order, or in place you're going to need extra storage if you get stability. So this concludes our lecture on the slower sorting algorithms.